The next thing is, do you fix the problem in hardware or software? I mean, surely it's easy to just create another few VMs or build some more servers. And that's cheap too. It's cheaper than people's time, surely. The problem is, fixing a problem in hardware is not a long-term solution. For example, on our databases, we used to run on Sun Spark boxes, and every year we'd upgrade to the latest and greatest. The problem with this is, a few years ago, I think in 2006, we got stuck on one server. We couldn't go to the biggest one, the next one up, because it would actually slow things down due to the latency within its architecture. So we were stuck on this server. We didn't have anything else to migrate to, and had to resort to software improvements to help here. It wasn't until the large multi-core Optron and Xeon boxes came available that we could change. So we were on the same hardware for over 5 years on the databases. Despite this, peak load was going down over time, despite the increase in load that you've already seen. This demonstrates the importance of fixing problems in software. Again, on the application stack, is critical too, because Moore's law is not enough. And whilst you can always buy more and more servers, this comes with additional operational and management overheads, which we like to avoid. So typically, when we detect a problem, or a potential problem, we'll throw more hardware at it to try to alleviate the problem. But then we'll also open up a ticket or a JIRA and look to address the problem properly in software, because it's the only way in which we can scale. Again, monitoring is key to early detection of this, because without it, the first thing you know about it is customers are calling up and complaining. So talking about clouds is something that many people talk to help them with scale, because you have an almost infinite and limitless opportunity of scaling sideways. However, this can't work for us, or at least not for our whole sports exchange, due to regulation and compliance reasons. We do still use clouds for various things, particularly on the front end, and this has been quite helpful. And internally, we use virtualization significantly. The other thing about clouds, which sometimes gets forgotten, is that you can get huge variances in latencies within the cloud, even comparing one day to the next. And our applications are designed around low latency because this is what our customers expect. So anyway, I mentioned we're using virtualization internally, and we're getting some benefits from it. In fact, through combining virtualization with infrastructure automation, we're getting many of the benefits of a cloud internally, although I wouldn't quite call it that, because we're not there yet. And as such now, I think over 50% of our production infrastructure and about 90% of our development environments are all automated. Are all virtualized, sorry. So moving on to monitoring, which is something I've been talking about quite a lot. With monitoring, customers' expectations as the web matures are increasing, especially around performance, reliability and uptime. As such, what was okay a few years ago is no longer good enough. Standing still is definitely going backwards. And especially if you combine this with the explosion of applications and services that we're seeing within our environment. When we started out with monitoring, we had simple web things which would maybe check the functionality of applications. These might just check one piece of code, or check if an underlying database or other component was there. Or in some cases, for one of our previous poker products, all it would do is always return OK. It didn't even bother doing any checking. This sucked. So we then attempted to improve this by synthesizing user requests, attempting to recreate user behavior. But this was quite slow and led to some false positives. So we improved again. We introduced passive monitoring, looking at the applications for errors that real customers were seeing. This would give us more accuracy, surely. But the problem this gave us was that servers would be taken out of service because of a few customer errors. And there was nothing to add them back into service later if the problem had gone away. This would require manual intervention. So we iterated again. We introduced active monitoring, combining some of the synthetic behavior with the passive monitoring. But this was still JVM-centric, and would only work for applications which we've written. And even amongst the applications we'd written, it would require refactoring of many of them and rewriting of others in order to get them compliant. So we still ended up in a situation where we had different methods of debugging applications which were developed by different teams. And, with the number of applications we now need to support, this was not sustainable. So we needed to look for a new approach. And with Java 1.5, Sun introduced the Java agent functionality, which enables lightweight profiling. This enables you to treat a transaction as an identifier, which enables a more customer-centric approach. By business transaction, at Betfair, this is, for us is simply a customer request on a web page. For example, viewing a market, logging in, placing a bet would be 3 examples of this. These are what matter, not some internal metrics about whether some method is faster or slower than yesterday, because these are actually what the customers are seeing. Furthermore, this is enabling the same language to be used between product and technical people, as login is login. And also, as we're doing our platform rewrites, we're changing the underlying code. But a login is still a login, so we can track improvements over time. So we identified that this would be a good way of monitoring, but we didn't know how to do it. So we set about defining our key requirements. We're quite demanding in this way. For example, any tool must work, must be useful, and help us solve problems. And it must be real-time, because as I've already mentioned, we are a real-time business. Key things on top of this, and going from the bottom upwards, is it must be low latency. We spend a lot of time and effort making our application fast, so we don't want to slow it down again. Similarly, we wanted to have an automated setup, as with hundreds of applications, manual configuration would be timely and would result in shelfware. It must be easy to use, as otherwise people won't use it. They'll go back to using the old methods. And it must have a low CPU overhead, because otherwise we'll have to buy more servers, and we don't want to do that. And on top of this, and finance will probably want this further down, it must be affordable, because otherwise you can only use it in key areas. And we want to use the same tool for everything. And of course, like any tool, it must be sexy. We want the pretty graphs, the snazzy graphics. I know, that's what it's all about, surely. So we started looking around for a solution. We did proof of concepts, and even looked at creating our own. It kind of seemed like a Goldilocks problem, where we were trying out different bowls of porridge, and nothing seemed just right. One was too hot, one was too cold, one was too slow, one was too something else, whatever. And yeah, we couldn't find anything. So that was until 2010, when we came across App Dynamics, and they looked pretty mixed. But before we want to talk about that, I'll talk you through our old troubleshooting process, which I'm sure will be familiar to many of you. A call will come into the help desk from the customer, complaining that something was slow or was not working. This would get escalated to our NOC, and then out to the component owners. This would begin a fire drill where we'd run through the problem, looking for a solution, and checking logs and so on. Developers couldn't have production access due to the regulatory reasons I've already mentioned, because we have to have a separation of privileges. This would mean logs would often get sent out to developers after being sanitised, or they would end up looking over an ops person's shoulder. This was pretty inefficient. And we also noticed that on pretty much every outage, we'd have the same group of people, or at least the same similar people each time. We had real key man dependencies. And this created problems when people were off sick or on holiday. So we needed to fix this, and we recognised it was a problem. So looking at a problem, looking at as a transaction from App Dynamics' point of view, I picked a relatively complicated one because then we can find out more information about it. A kind of key thing here is not the fact it's real time, or almost. It's about one or 2 minutes behind. The first thing you'll see in the middle of the graph, the middle of the page, maybe you can't, is we've got three items. We have on the right, where it says start, the public API, which is the applications here. It then has automatically detected connectivity to some databases and to a message queue. We're using this particularly for some of our new applications, the SOA ones, to build connectivity matrices of how the applications are connected, and to build firewall configuration based on this. You can see at the top right-hand corner, we've got a big green tick. This means it's healthy. There haven't been any problems detected in the last day. And you can see down the bottom in the graphs, the request rate in blue so drops off as we go into night and climbs back up again the next morning. You can also see that the response times increase overnight. This is because of the way our caching works. It's more efficient with more load. The other key thing here as well, because is dynamics builds up automatic baselining over time. That is, it looks at response times compared to the previous day, the previous week, the previous month, and builds up patterns based on that to reduce the number of false positives. So despite the fact this transaction is actually looking healthy, in general, you might be able to see, actually probably not, that we've had 0.1% of transactions which are very slow. And we want to look into this. So with this, it's almost a one-click operation to be able to do this. And you can drill down into a slow transaction. Well, within this, you can see the call graph. So you can see the class and method being called, all the way down to the line of code, which is ideal for developers. To see what's going on. Additionally, it's exposing just the performance metrics. That is, thus enabling us to have the same tool being used by both developers and ops people. It's pretty lightweight. The calls under 10 milliseconds aren't instrumented, which for us can get frustrating because we have many calls less than that, and we want to know how to make them faster. But anyway, in this one, you can see down at the bottom, about 50% of the time is being spent talking to the databases, and we want to look into this. So what we're able to do is follow it through. I probably should include some more screenshots, but you can pull out the SQL statement being run and the length of time that's been taken. In this case, it's something to do with user profile. Here we have yet another trick up our sleeves, DB Tuner. I won't talk about that too much today because I'm here to talk about applications. But think of DB Tuner as a bit like AppDynamics for databases. The integration between the two of them is currently manual, although we're hoping the DB Tuner guys and AppDynamics guys will work together to integrate this. So, back a couple of slides ago, I had a big triangle up there which showed our requirements. And the key thing there was latency. The first thing we did during our proof of concepts, when we were testing out when we were recreating outage scenarios and other things, we would compare the latency under load with and without dynamics. And we were happy that it wasn't going to affect performance. Despite this, some of the developers were still skeptical. So what we did when we went live with dynamics in production is for some of the new applications, in this case, LRO, Exchange Read Only, and MGA, the Market Global Service, we enable transaction monitoring for some loads, but not all. And this enables us to compare the effects of them over time. So you can see on the left, with ERO, the graphs both with AppDynamics in orange, and without AppDynamics in blue, the usage is the same. And you can see underneath, in the network graph, that the traffic is the same too. On the right, for Market Global, CPU usage is slightly up, but then you can also see that the network traffic is significantly up too. I probably need to look into that, because there may be an issue with our load balancing.